Imagine looking into the night sky and realizing that somewhere out there exists an object so powerful that it releases more energy than hundreds of billions of stars combined. Not in a brief flash, not in a violent explosion, but steadily, continuously, for millions of years. This object is not a galaxy, even though it can outshine one. It is not a supernova, even though it is far more energetic. It is not a star, even though it may appear like one through a telescope. In fact, this object can be smaller than our solar system, yet it can dominate its entire region of space with light so intense that it can be detected from billions of light years away. This object is known as a quasar, and its existence challenges some of the most basic assumptions we make about size, power, and scale in the universe. When people first hear about quasars, the reaction is usually disbelief. How can something small overpower something vast? How can a single object compete with an entire galaxy filled with billions of stars, each burning with nuclear fire? In our everyday experience, power usually grows with size. A larger engine produces more force. A larger fire produces more heat and light. A larger city glows brighter at night. Our brains are wired to associate size with strength. But the universe does not follow human intuition. In space, the relationship between size and power is far more complex, and quasars are one of the clearest examples of how misleading our instincts can be. The mystery of quasars begins with how they were first observed. When early radio telescopes scanned the sky in the mid-20th century, astronomers detected strange, intense radio signals coming from deep space. These signals did not match anything known at the time. When scientists tried to locate their source using optical telescopes, they found what looked like faint stars. But something was wrong. These star-like points of light did not behave like stars. They were far too bright for their apparent size, and their light carried unusual spectral signatures that did not fit existing models. At first, many astronomers suspected errors in their instruments or calculations. The idea that such small-looking objects could be so powerful seemed unreasonable. As technology improved and measurements became more precise, the confusion only deepened. The distances involved were staggering. These objects were not located within our galaxy or even nearby galaxies. They were located billions of light years away, meaning the light reaching Earth had been traveling through space for billions of years. When scientists calculated how bright these objects must actually be at their source, the numbers were shocking. The energy output required was greater than anything previously observed in the universe. It was so extreme that it forced astronomers to confront a disturbing possibility. Either the laws of physics were incomplete, or the universe contained objects far more extreme than anyone had imagined. This was not a small scientific disagreement. The discovery of quasars triggered intense debate. Some researchers argued that the distances must be wrong. Others suggested entirely new forms of matter or unknown energy sources. But as more quasars were discovered and studied, the evidence became impossible to ignore. These objects were real, they were incredibly distant, and they were releasing energy on a scale that defied conventional explanations. The universe, it seemed, was far more violent and powerful than previously believed. The name quasar itself reflects this early confusion. It comes from the term quasi-stellar radio source, which means something that looks like a star but behaves very differently. This name captures the central mystery perfectly. Quasars appear point-like, similar to stars, yet they are not stars at all. They are not even individual objects in the traditional sense. Instead, they are the visible result of an extreme process occurring at the heart of a galaxy. Understanding this distinction is crucial, because it explains why quasars are often misunderstood as being the biggest objects in space when, in reality, their power comes from concentration, not size. To truly understand quasars, we must shift our thinking away from physical size and toward energy density. A quasar does not fill space the way a galaxy does. It does not stretch across hundreds of thousands of light years. Instead, Its brilliance comes from a relatively small region where matter is being forced into one of the most extreme environments known to science. This environment exists around a supermassive black hole, an object with a gravitational pull so strong that it can trap light itself. These black holes can be millions, or even billions, of times more massive than the Sun, yet they occupy a region of space that is astonishingly compact. When vast amounts of gas and dust fall toward a supermassive black hole, they do not immediately disappear beyond the point of no return. Instead, they spiral inward, forming a rapidly rotating disk of material. As this material accelerates, it heats up to extraordinary temperatures, releasing enormous amounts of energy in the form of light, X-rays, and other radiation. This glowing disk, along with powerful jets of energy shooting out from the black hole's poles, is what we observe as a quasar. The black hole itself remains invisible, but its influence creates one of the brightest phenomena in the universe. This process is incredibly efficient. Nuclear fusion, which powers stars, converts only a small fraction of mass into energy. Gravity, when matter falls into a black hole, can convert a much larger fraction of mass into energy. This is why a quasar can outshine trillions of stars while being physically much smaller than a galaxy. It is not that quasars break the laws of physics, but rather that they operate in a regime where gravity becomes an extraordinarily powerful energy source. Because quasars are so luminous, they can be observed across vast cosmic distances. Many of the quasars we see today existed when the universe was very young, only a few billion years old, or even less. Their light began its journey long before Earth existed, long before the Sun formed, and long before life emerged. When we observe a quasar, we are not seeing it as it is now. We are seeing it as it was billions of years ago. This makes quasars invaluable tools for studying the early universe. They act like cosmic beacons, illuminating regions of space that would otherwise remain dark and unreachable. This time travel aspect of quasars adds another layer to their mystery. They allow astronomers to study the conditions that existed when galaxies were forming and evolving. By analyzing quasar light, scientists can learn about the composition of early galaxies, the distribution of matter in the universe, and the processes that shaped cosmic history. In this sense, quasars are not just powerful objects. They are windows into the past, offering clues about how the universe became what it is today. Despite their importance, quasars are often misunderstood and sensationalized. Their extreme energy output leads some people to imagine them as cosmic threats, capable of destroying everything in their path. While it is true that quasars can influence their surrounding galaxies, they are not roaming destroyers. They are fixed to the centers of galaxies, and their effects are governed by distance and direction. Most quasars are so far away that their energy poses no danger to us. In fact, the closest quasar to Earth is still hundreds of millions of light years away, far beyond any realistic threat. Another important point is that quasars are temporary. They do not shine forever. As the supply of matter around a supermassive black hole is consumed or dispersed, the quasar gradually fades. The galaxy settles into a quieter state, and the once blazing core becomes dormant. Our own galaxy likely went through a quasar phase in its distant past, but today its central black hole is relatively calm. This means that quasars represent a phase in galactic evolution, not a permanent feature of the universe. This brings us back to the central question that inspires so much curiosity and confusion. Are quasars really the biggest objects in space? The answer depends on what we mean by big. If we mean physical size, then no. Quasars are not the largest structures in the universe. Galaxies, galaxy clusters, and vast cosmic filaments extend across incomprehensible distances and contain far more matter. But if we mean energy output and brightness, then quasars stand at the very top. They are the brightest sustained objects ever observed, capable of outshining entire galaxies despite their compact size. Understanding this distinction is essential because it reveals something profound about the universe. Power does not always come from size. Sometimes it comes from extreme conditions concentrated into a small region. Quasars teach us that the universe can produce astonishing effects when matter, gravity, and energy interact in the right way. They remind us that the cosmos is not just vast, but also deeply strange and full of surprises. In the journey ahead, we will explore how quasars were discovered in more detail, how scientists finally understood their true nature, and how they compare to the largest structures in existence. We will examine the black holes that power them, the galaxies that host them, and the role they play in shaping the universe. By the end, the mystery of quasars will no longer feel overwhelming, but their awe-inspiring nature will remain. This is not just a story about extreme objects in space. It is a story about how the universe challenges our assumptions and forces us to see reality in new ways. The story of quasars does not begin with clarity or excitement, but with confusion and doubt. In the early 20th century, astronomers believed they had a fairly solid understanding of the universe. They knew about stars, nebula, galaxies, and the general structure of the cosmos. While many mysteries remained, there was confidence that new discoveries would fit into existing frameworks. No one expected to find something that would completely disrupt their understanding of how energy, distance, and brightness worked in space. Yet that is exactly what happened when scientists began listening to the universe instead of just looking at it. The first hints of quasars came not from visible light, but from radio waves. In the 1930s and 1940s, astronomers developed radio telescopes capable of detecting invisible signals coming from space. These instruments revealed a universe that looked very different from the one seen through optical telescopes. Suddenly, the sky was filled with intense radio sources, many of which had no obvious visual counterpart. Some of these signals were so strong that they rivaled emissions from the entire Milky Way galaxy. At the time, no one knew what could produce such powerful radio waves. As radio astronomy advanced, scientists began mapping these mysterious radio sources more precisely. They expected to find that most of them were associated with known objects, such as supernova remnants or nearby galaxies. But a small group of radio sources stood out. They were incredibly compact, meaning the radio emissions appeared to come from a very small region of space. Even more strangely, when astronomers pointed optical telescopes at their locations, they did not see galaxies or clouds of gas. Instead, they saw what looked like faint stars. This created a serious problem. Stars simply could not produce radio emissions of that strength. Even the most energetic stars known could not explain the observed signals. At first, scientists assumed the objects must be relatively close, perhaps within our own galaxy. If they were nearby, their brightness would not require impossible amounts of energy. This assumption seemed reasonable, and for a while it was accepted without much resistance. However, as astronomers studied the light coming from these objects more carefully, another surprise emerged. The spectral lines, which act like fingerprints for elements, did not match anything familiar. They appeared shifted, stretched toward longer wavelengths. This effect, known as redshift, is a key indicator of distance in the universe. The greater the redshift, the farther away an object is moving from us due to the expansion of the universe. When scientists finally interpreted these spectral lines correctly, the results were shocking. These objects were not nearby at all. They were incredibly distant, located billions of light years away. This realization turned a minor puzzle into a full-scale crisis. If these objects were truly that far away, then their brightness could not be explained by any known process. To be visible across such vast distances, they would need to emit more energy than entire galaxies. The idea seemed absurd. Many astronomers refused to accept it. Some argued that the redshift interpretation must be wrong. Others proposed exotic explanations involving unknown physics or errors in measurement. The scientific community was deeply divided. One of the turning points came in the early 1960s, when astronomers precisely identified the radio source, known as 3C273. When its spectrum was finally decoded correctly, it became clear that this object was located far beyond our galaxy. The energy output implied by its brightness was staggering. There was no escaping the conclusion. The universe contained objects capable of releasing energy on a scale that had never been imagined before. These objects were later named quasars, short for quasi-stellar objects, reflecting their star-like appearance combined with their extraordinary behavior. The reaction was intense. Scientific papers debated whether such objects could exist at all. Some researchers suggested that quasars might be powered by chains of supernova explosions. Others speculated about unknown forms of matter or entirely new physical laws. But none of these explanations held up under scrutiny. The energy requirements were simply too high. Even the combined explosion of thousands of supernovae could not sustain the continuous output observed in quasars. As more quasars were discovered, patterns began to emerge. They were almost always found at great distances, meaning they were more common in the early universe than they are today. This suggested that quasars were linked to a specific era in cosmic history. They were not random anomalies, but a natural part of how galaxies formed and evolved. This insight was crucial because it shifted the question from whether quasars existed to why they existed. Gradually, a new idea gained traction. Instead of being exotic stars or chains of explosions, quasars might be powered by something far more extreme. Astronomers began to consider the role of black holes, which until then were largely theoretical objects. The idea that black holes could exist at the centers of galaxies was controversial, but it offered a possible solution. A supermassive black hole consuming vast amounts of matter could in principle release the required energy. This process would not rely on nuclear fusion, but on gravitational energy, which is far more efficient. At first, this idea seemed just as unbelievable as the quasars themselves. Black holes were thought of as simple gravitational traps, not engines capable of producing enormous amounts of light. But as theoretical models improved, it became clear that matter falling toward a black hole could heat up dramatically, forming a luminous disk and emitting powerful radiation. This mechanism matched many of the observed properties of quasars, including their brightness, variability, and spectral signatures. Still, acceptance was slow. Science advances through evidence, not imagination, and astronomers demanded proof. Over time, observations across different wavelengths began to confirm the black hole model. X-ray emissions, rapid fluctuations in brightness, and the presence of powerful jets all pointed toward compact, massive engines at the centers of quasars. These observations ruled out large, diffuse sources of energy and supported the idea of a concentrated power source. By the late 20th century, the debate had largely settled. Quasars were understood as active galactic nuclei, powered by supermassive black holes consuming surrounding matter. This realization marked a turning point in astronomy. Black holes were no longer theoretical curiosities. They were real, common, and central to the evolution of galaxies. Quasars became one of the strongest pieces of evidence for their existence. Yet even as their nature became clearer, quasars continued to raise new questions. Why were they so common in the early universe, but rare today? How did black holes grow so massive so quickly? How did quasar activity affect the formation of stars and galaxies? These questions opened new fields of research and reshaped our understanding of cosmic history. The discovery of quasars also changed how astronomers viewed the universe as a whole. It revealed that the cosmos was not a calm, slowly evolving place, but a dynamic and sometimes violent environment. Enormous amounts of energy could be released in relatively small regions of space, driven by processes that challenged human intuition. This realization forced scientists to rethink their assumptions about what was possible. Perhaps most importantly, quasars taught astronomers humility. They showed that even confident scientific models could be overturned by new observations. The universe was not obligated to behave in ways that made sense to us. Instead, it followed its own rules, waiting for curious minds to uncover them. The confusion surrounding quasars was not a failure of science, but a demonstration of its strength. Through careful observation, debate, and revision, astronomers gradually transformed mystery into understanding. As we move forward in this journey, the focus will shift from discovery to explanation. Now that we know quasars are real and understand where they come from, the next step is to explain what they truly are in simple terms. What exactly is happening at the heart of a quasar? How does a black hole produce so much light? And why does this process make quasars appear so powerful compared to everything else in the universe? These are the questions we will explore next as we finally break down the true nature of quasars and the extreme physics that power them. To truly understand what a quasar is, we must first clear away some common misunderstandings. A quasar is not a star, even though it may look like one through a telescope. It is not a single object floating alone in space, and it is not a type of galaxy either. A quasar is best understood as an extremely energetic phase in the life of a galaxy, a moment when the galaxy's core becomes so active that it overwhelms everything else around it with light and energy. This distinction is important because many of the myths surrounding quasars come from treating them as ordinary objects rather than as powerful cosmic processes. At the heart of every quasar lies a galaxy. This galaxy may be young or in the middle of violent interactions, such as collisions or mergers with other galaxies. In the center of that galaxy sits a supermassive black hole, an object with mass millions or even billions of times greater than the Sun. On its own, this black hole does not shine. It does not glow or emit light. In fact, it is completely dark. But the environment around it can become one of the brightest regions in the universe when the conditions are right. The key to a quasar's power is matter. Galaxies are filled with gas, dust, and stars. When large amounts of gas are driven toward the galaxy's center, often due to gravitational disturbances, like mergers or close encounters with other galaxies, this material begins to fall toward the supermassive black hole. But instead of falling straight in, the gas starts to orbit the black hole at incredible speeds. This motion creates what is known as an accretion disk, a flattened spinning structure made of superheated matter. As material in the accretion disk spirals inward, it rubs against itself, compresses, and accelerates. These processes generate enormous heat. Temperatures rise to millions of degrees, causing the disk to glow intensely across multiple forms of radiation, including visible light, ultraviolet rays, and X-rays. This glowing disk is the main source of the quasar's brightness. It is not the black hole itself that shines, but the violent activity surrounding it. In some quasars, this activity becomes even more extreme. Powerful jets of charged particles are launched from regions near the black hole's poles, traveling at speeds close to the speed of light. These jets can extend far beyond the galaxy itself, interacting with surrounding intergalactic space. While not all quasars produce prominent jets, those that do are among the most energetic phenomena ever observed. These jets further contribute to the quasar's influence on its environment. This explains why quasars appear so bright despite being physically compact. The region producing the light may be no larger than our solar system, yet it releases more energy than entire galaxies. This concentration of power is what makes quasars so unique. They do not rely on vast numbers of stars spread across space. Instead, they focus enormous energy into a small area, driven by gravity and motion rather than nuclear fusion. It is also important to understand that quasars are temporary. A galaxy does not remain a quasar forever. The quasar phase begins when there is an abundant supply of matter falling into the black hole. Over time, this supply decreases. Gas is either consumed, blown away by radiation, or settles into a quieter state. As the inflow of material slows, the accretion disk dims, the jets weaken, and the quasar fades. The galaxy then appears more ordinary, even though the supermassive black hole remains at its center. This idea helps explain why quasars are far more common in the distant universe than they are nearby. When the universe was younger, galaxies were closer together and more likely to collide or interact. These interactions funneled large amounts of gas toward galactic centers, triggering intense quasar activity. As the universe expanded and galaxies settled into more stable configurations, such extreme activity became rarer. Today, most galaxies, including our own, host relatively quiet black holes. Another point of confusion arises from how quasars are observed. Early telescopes lacked the resolution to distinguish between a quasar and a star-like point of light. This is why quasars were originally mistaken for stars. Modern instruments, however, reveal that quasars are embedded within galaxies. The galaxy itself may be faint compared to the quasar's brightness, but it is always there. This confirms that quasars are not isolated objects, but part of larger galactic systems. Understanding what a quasar is also requires understanding what it is not. A quasar is not a type of explosion. It does not erupt and disappear like a supernova. Instead, it shines steadily for millions of years. It is not a star burning fuel in its core. It is not a cloud of gas collapsing under its own gravity. It is a gravitational engine, converting the motion and heat of infalling matter into radiant energy with remarkable efficiency. This efficiency is one of the most important features of quasars. Stars convert only a small fraction of their mass into energy through nuclear fusion. Black hole accretion can convert a much larger fraction of mass into energy. This means that even a relatively small amount of matter falling into a supermassive black hole can produce an extraordinary amount of light. This is why quasars can outshine galaxies despite being so compact. Because of their brightness, quasars can be detected across immense distances. They serve as markers for the early universe, allowing astronomers to study conditions that existed billions of years ago. By analyzing quasar light, scientists can learn about the composition of intergalactic space, the distribution of matter, and the processes that shaped early galaxies. Quasars act as backlights, illuminating everything between them and us. Despite their immense power, quasars are governed by the same physical laws that apply everywhere else in the universe. There is no exotic or supernatural energy involved. Gravity, motion, heat, and radiation are enough to explain their behavior. What makes quasars extraordinary is not that they break the rules, but that they push those rules to their extremes. This brings us back to one of the most common misconceptions about quasars: the idea that they are the biggest objects in space. In terms of physical size, quasars are not large at all. The region producing the quasar's light is tiny compared to a galaxy. However, in terms of energy output per unit volume, quasars are unmatched. This distinction between size and power is crucial for understanding their true nature. To summarize in simple terms, a quasar is a galaxy whose central black hole is actively consuming matter at a very high rate. The energy released by this process produces an intense glow that can outshine the galaxy itself. This phase is temporary and depends on the availability of fuel. When the fuel runs out, the quasar fades, leaving behind a quieter galaxy with a dormant black hole at its center. In the next part of this journey, we will focus more deeply on the true engine behind quasars, the supermassive black holes themselves. We will explore how massive they are, how they form, and how something that emits no light can be responsible for some of the brightest objects in the universe. Understanding the black hole is essential because it holds the key to why quasars behave the way they do and why their power seems almost impossible. To understand why quasars are so powerful, we must face the object at their core, an object that does not shine, does not glow, and cannot be seen directly, yet controls everything around it. This object is a supermassive black hole, and despite its popular image as a cosmic vacuum cleaner, it is something far more subtle and far more extraordinary. A black hole is not a hole in space in the everyday sense. It is a region where gravity has become so strong that the normal rules of matter and light begin to fail. When a black hole becomes supermassive, its influence extends across vast regions of a galaxy, shaping its structure, its evolution, and in the case of quasars, its brilliance. Black holes begin their existence in relatively humble ways. Many form when massive stars reach the end of their lives and collapse under their own gravity. These stellar black holes are powerful, but they are small on cosmic scales. A supermassive black hole, however, is something entirely different. It contains the mass of millions or even billions of suns, yet it is compressed into a region of space that may be no larger than our solar system. How such objects form is still an active area of research, but what is clear is that they exist at the centers of almost all large galaxies, including our own Milky Way. What makes a black hole black is the event horizon, a boundary beyond which nothing can escape, not even light. But it is important to understand that most of a black hole's influence happens outside this boundary. Matter does not suddenly vanish the moment it approaches a black hole. Instead, it experiences increasing gravitational forces that stretch, heat, and accelerate it. This is where the true power of a quasar is generated. The black hole itself does not produce energy. The energy comes from the journey matter takes as it falls toward the black hole. As gas and dust are pulled inward by gravity, they begin to orbit the black hole rather than falling straight in. This motion creates an accretion disk, a swirling structure of matter moving at incredible speeds. Friction within this disk causes temperatures to rise dramatically. At these temperatures, matter emits enormous amounts of radiation. This radiation is what we observe as the blinding light of a quasar. In other words, the quasar is not the black hole. It is the storm of energy created by matter struggling against gravity just before it disappears forever. The scale of this process is difficult to grasp. A supermassive black hole can consume the equivalent of several suns worth of material every year during its most active phase. As this material spirals inward, a significant fraction of its mass is converted directly into energy. This conversion is far more efficient than nuclear fusion, which powers stars. In a star like the Sun, less than 1% of mass becomes energy. Near a black hole, that fraction can be many times higher. This is why quasars can produce such astonishing brightness without needing vast physical size. One of the most striking features associated with supermassive black holes in quasars is the presence of relativistic jets. These jets are narrow beams of particles and energy launched from regions close to the black hole, traveling at speeds approaching the speed of light. They extend far beyond the accretion disk and can stretch across distances larger than the host galaxy itself. While not all quasars have visible jets, those that do demonstrate just how focused and directional black hole-powered energy can be. These jets can heat surrounding gas, influence star formation, and reshape entire regions of intergalactic space. Despite their fearsome reputation, black holes are not actively hunting nearby matter. A black hole only consumes material that comes close enough to be captured by its gravity. If the Sun were replaced by a black hole of the same mass, the planets would continue orbiting in much the same way. What makes supermassive black holes so effective at powering quasars is not that they pull harder, but that they are surrounded by vast reservoirs of matter, especially in young or interacting galaxies. When large amounts of material are available, the black hole becomes an engine of light. The relationship between a galaxy and its central black hole is deeply interconnected. Observations have shown that the mass of a supermassive black hole is closely linked to the mass and structure of its host galaxy. This suggests that galaxies and black holes grow together, influencing each other over cosmic time. During the quasar phase, this relationship becomes especially intense. The energy released by the quasar can heat or expel gas from the galaxy, slowing or even stopping star formation. In this way, the black hole does not just feed on the galaxy, it also regulates the galaxy's future. This feedback process helps explain why quasars do not last forever. As the black hole consumes matter and releases energy, it eventually disrupts the very supply that fuels it. Gas is blown away or heated to the point where it can no longer fall inward efficiently. The accretion disk thins, the radiation weakens, and the quasar fades. What remains is a quieter galaxy with a dormant, supermassive black hole at its center. The monster falls asleep, but it never disappears. Understanding supermassive black holes also requires addressing the question of scale. When people imagine something that powers a quasar, they often imagine a massive object filling space like a giant sun. In reality, the black hole itself occupies a surprisingly small region. Its gravitational reach is vast, but its physical size is compact. This again highlights why quasars confuse our intuition. Their power comes not from occupying large volumes of space, but from concentrating extreme conditions into a small area. The growth of supermassive black holes remains one of the great mysteries of modern astronomy. Some appear to have reached enormous masses very early in the universe's history, only a few 100 million years after the Big Bang. This raises difficult questions. How did they grow so quickly? Did they form from the collapse of massive primordial clouds, or did they grow from smaller black holes through rapid accretion and mergers? Quasars provide crucial clues because their brightness allows us to observe these black holes in the distant past. Every observation of a quasar is also an observation of a black hole in action. By studying quasar light, astronomers can infer the mass of the black hole, the rate at which it is consuming matter, and the structure of the surrounding disk. This has turned quasars into laboratories for studying extreme physics. Conditions near a black hole push matter, energy, and space itself to their limits, offering insights into gravity that cannot be replicated on Earth. It is important to emphasize that supermassive black holes are not anomalies. They are common features of the universe. Almost every large galaxy studied contains one at its center. What is rare is the quasar phase, the moment when the black hole is actively feeding at a high rate. This distinction helps demystify quasars. They are not exotic exceptions. They are ordinary galaxies caught in an extraordinary moment. This understanding also reframes the question of whether quasars are the biggest objects in space. The black hole powering a quasar may be incredibly massive, but it is not physically large compared to cosmic structures like galaxies or clusters of galaxies. The quasar's brilliance can dominate perception, making it seem enormous, but its true scale is defined by concentration rather than extent. The monster at the center is powerful because it is compact, efficient, and fed by gravity's relentless pull. As we move forward, the focus will shift from the engine itself to the result of its activity. In the next part, we will explore why quasars are the brightest objects ever observed, how their energy output compares to stars and galaxies, and why their light can travel across the universe to reach us. Understanding the black hole explains how quasars are powered. Understanding their brightness explains why they capture our attention and challenge our understanding of cosmic scale. When people hear that quasars are the brightest objects in the universe, the statement often feels exaggerated, almost unbelievable. After all, the universe contains countless stars, enormous galaxies, and violent explosions like supernovae and gamma-ray bursts. How could a single source of light overpower so much cosmic activity? To understand this, we must move beyond simple comparisons and examine how energy is produced, concentrated, and released in space. The brightness of a quasar is not an accident, and it is not the result of sheer size. It is the outcome of an extraordinarily efficient process operating under extreme conditions. Brightness in astronomy is not just about how much light something produces, but how that light compares to other sources and how far it can travel. A candle is faint, but from across a dark room it is visible. A city is bright, but from space it becomes a small glow. In the universe, distances are so vast that even extremely powerful objects can become invisible if their light spreads out too much. Quasars defy this problem because they release so much energy that even after traveling billions of light years, their light remains detectable. This alone places them in a category unlike most other cosmic objects. To grasp why quasars shine so intensely, it helps to compare them with stars. A star like the Sun produces energy through nuclear fusion. In its core, hydrogen atoms fuse together to form helium, releasing energy in the process. This reaction is incredibly powerful by human standards, but it is surprisingly inefficient on a cosmic scale. Only a small fraction of the mass involved in fusion is converted into energy. Most of the mass remains locked inside the star. This limits how bright a star can be, no matter how large it grows. A quasar, on the other hand, is powered by gravity, not fusion. When matter falls toward a supermassive black hole, it releases gravitational energy as it accelerates and heats up. This process can convert a much larger fraction of mass into energy than nuclear fusion ever could. The result is a level of brightness that stars simply cannot match. Even the combined light of billions of stars in a galaxy can be overshadowed by the energy released in the region around a feeding black hole. Another important factor is concentration. A galaxy spreads its light across vast distances. Its stars are separated by enormous gaps of space, and their combined light is distributed across hundreds of thousands of light years. A quasar concentrates its energy into a region that may be only a few light days or light weeks across. This concentration dramatically increases the intensity of the light. From a distance, this makes the quasar appear incredibly bright, even though it occupies a much smaller physical volume than a galaxy. The accretion disk around a supermassive black hole plays a central role in this process. As matter spirals inward, it forms a flattened disk that rotates at tremendous speeds. Friction, compression, and magnetic forces within this disk generate extreme temperatures. These temperatures cause the disk to emit light across a wide range of wavelengths, from visible light to ultraviolet and X-rays. This broad emission makes quasars visible to many different types of telescopes, increasing their apparent brightness across the electromagnetic spectrum. In addition to the accretion disk, many quasars produce powerful jets that contribute to their luminosity. These jets focus energy into narrow beams that can extend far beyond the host galaxy. When one of these jets happens to point toward Earth, the quasar appears even brighter due to a phenomenon known as relativistic beaming. This effect occurs because the particles in the jet are moving at speeds close to the speed of light, causing their radiation to be compressed and intensified in the direction of motion. While not all quasars are oriented this way, those that can appear especially dazzling. The sheer scale of a quasar's energy output is difficult to fully comprehend. Some quasars release as much energy per second as thousands of galaxies, like the Milky Way combined. This energy is not released in a single burst, but continuously over millions of years. This sustained output sets quasars apart from transient events, like supernovae, which may briefly outshine an entire galaxy but fade quickly. For quasars' endurance makes its brightness even more remarkable. Distance also plays a role in how we perceive quasars. Many of the brightest quasars observed are located at extreme distances, meaning their light has been stretched and dimmed by the expansion of the universe. Despite this, they still appear as some of the brightest objects in the sky at their wavelengths. This implies that at their source they are even more powerful than they appear to us. When astronomers correct for distance and cosmic expansion, the true luminosity of quasars becomes almost staggering. This extreme brightness is why quasars were once mistaken for stars. Early telescopes could not resolve the faint galaxies hosting these objects, leaving only the brilliant core visible. Even today, separating the light of a quasar from its host galaxy can be challenging. The quasar often dominates the galaxy's appearance, making the surrounding stars seem insignificant by comparison. This dominance reinforces the idea that quasars are somehow larger or more substantial than they truly are. It is also worth noting that brightness does not necessarily imply permanence. Quasars are bright because they are active. Their brightness depends on the rate at which matter is falling into the black hole. When this rate decreases, the quasar dims. This variability has been observed in many quasars, which can change in brightness over relatively short timescales. These changes provide important clues about the size of the emitting region, since rapid variations imply a compact source. This again confirms that quasars achieve their brightness through concentration, not size. Comparisons with other extreme objects help put quasar brightness into perspective. Supernovae are among the most powerful explosions in the universe, releasing enormous amounts of energy in a short time. Gamma-ray bursts are even more intense, but they last only seconds or minutes. Quasars, by contrast, are steady powerhouses. Their sustained output over millions of years results in a total energy release that far exceeds these brief events. This long-term brilliance is what makes quasars so influential in shaping their environments. The brightness of quasars also affects the space around them. Their radiation can heat surrounding gas, preventing it from forming new stars. In some cases, this radiation can drive powerful winds that push material out of the galaxy entirely. This feedback mechanism helps regulate galaxy growth and explains why some galaxies stop forming stars earlier than others. In this sense, quasar brightness is not just a spectacle, it is a force that shapes cosmic history. Understanding quasar brightness also requires acknowledging the limits of human perception. Our eyes are tuned to visible light, but quasars emit across a much broader range of wavelengths. Some of their most intense emissions occur in ultraviolet and X-ray wavelengths that are invisible to us. Specialized instruments are required to detect and study these emissions. When all wavelengths are taken into account, the total energy output of a quasar becomes even more impressive. Despite all of this, it is important to avoid a common misunderstanding. Brightness does not equal size. A quasar can dominate the light of a galaxy without dominating its mass or spatial extent. Galaxies contain far more matter and occupy far more space than quasars. The quasar's brightness can trick our intuition, making it seem like the most important or largest feature in the universe. In reality, it is one piece of a much larger cosmic structure. This distinction becomes crucial when we return to the central question of whether quasars are the biggest objects in space. In terms of luminosity, quasars sit at the top of the scale. Nothing else shines as brightly for as long, but in terms of physical size, they are surprisingly modest. The brilliance of quasars comes from efficiency and concentration, not from vast dimensions. The fact that quasars can outshine galaxies while being physically small is one of the most powerful lessons they offer. It reminds us that the universe does not measure importance by size alone. Energy, gravity, and motion can combine to produce effects that defy everyday logic. Quasars stand as extreme examples of this principle. challenging us to rethink how we define power in the cosmos. As we move forward, this understanding will help us answer the question that has been building throughout this journey. If quasars are not the biggest objects in space, what is? How do they compare to galaxies, galaxy clusters, and the largest structures ever discovered? To answer this, we must carefully separate brightness from size and explore the true giants of the universe. That exploration begins in the next part, where we directly confront the idea of cosmic bigness and finally put quasars into their proper place among the universe's most massive structures. By this point in the journey, it should be clear why quasars feel overwhelming. They shine brighter than galaxies, dominate their surroundings, and can be seen across nearly the entire observable universe. It is completely natural to assume that something so powerful must also be the biggest thing in existence. This assumption is repeated in articles, videos, and casual conversations about space. But to answer this question honestly, we must pause and define what we actually mean by big. In astronomy, size can mean many different things, and confusing these meanings is the root of almost every misunderstanding about quasars. When people say biggest, they often mean the object that feels the most extreme. Brightness feels extreme, power feels extreme, but physical size is a different measure entirely. Physical size refers to how much space an object occupies, how far it stretches from one end to the other. Mass is another measure, describing how much matter an object contains. Energy output is yet another, describing how much power it releases over time. Quasars score incredibly high in energy output, but that does not automatically make them the largest in size or mass. To put this into perspective, consider a simple analogy. A laser pointer can produce a very intense beam of light, bright enough to be seen from far away, but the device itself fits in your hand. A fog bank, by contrast, may cover an entire city but produce very little light. Intensity and size are not the same thing. Quasars are the cosmic equivalent of the laser pointer. They concentrate enormous energy into a small region, creating extreme brightness without occupying vast volumes of space. Physically, the region that produces a quasar's light is relatively compact. The accretion disk around a supermassive black hole may span a few light days or light weeks. Even when including the immediate surrounding structures, the active region remains tiny compared to a galaxy, which can stretch across hundreds of thousands of light years. This means that if you could somehow place a quasar next to a galaxy for comparison, the galaxy would dwarf it in size, even though the quasar would outshine it completely. This contrast becomes even more striking when we compare quasars to galaxy clusters. A galaxy cluster contains hundreds or even thousands of galaxies bound together by gravity. These clusters span millions of light years and contain enormous amounts of matter, including dark matter and hot gas. Compared to these structures, a quasar is almost insignificant in size. Yet a single quasar can still be bright enough to be detected from farther away than many entire clusters of galaxies. This again highlights how misleading brightness can be as a measure of size. Going even further, the largest known structures in the universe are not individual objects at all, but vast networks of matter known as cosmic filaments. These filaments form a web-like structure stretching across hundreds of millions of light years, connecting galaxy clusters and shaping the large-scale structure of the universe. These are truly the biggest structures known, dwarfing anything else in terms of spatial extent. Against this backdrop, a quasar is a tiny but brilliant spark within a much larger cosmic framework. So why does the idea persist that quasars are the biggest objects in space? Part of the answer lies in how we observe them. When early astronomers first studied quasars, they appeared as single, incredibly bright points of light. Their host galaxies were often invisible, drowned out by the quasar's glare. This made quasars seem isolated and dominant, reinforcing the impression that they were enormous objects rather than compact sources of energy within galaxies. Another reason is psychological. Human perception is strongly influenced by extremes. We remember the brightest, the loudest, and the most dramatic phenomena. Quasars dominate attention because they push the limits of what seems possible. When something outshines everything else, it feels natural to elevate it to the top of every category, including size. But science requires careful measurement, not intuition, and those measurements tell a very different story. This distinction becomes clearer when we examine mass. Supermassive black holes can indeed be incredibly massive, sometimes containing billions of times the mass of the Sun. However, even these giants are small compared to the total mass of a galaxy, which includes billions of stars, vast clouds of gas, and enormous amounts of dark matter. The black hole at the center of a quasar may be massive, but it typically accounts for only a tiny fraction of the galaxy's total mass. Again, power does not equal dominance in every category. It is also important to recognize that quasars are not permanent objects. They represent a phase of activity. When the fuel supply decreases, the quasar fades, but the galaxy remains. This temporary nature further separates quasars from truly large-scale structures, which persist over billions of years and define the architecture of the universe. Galaxies grow, merge, and evolve, but they do not suddenly switch off in the way quasars do. Understanding this helps clarify the real significance of quasars. Their importance does not come from being the biggest objects in space. It comes from what they reveal about extreme physics and cosmic evolution. Quasars show us what happens when gravity, matter, and energy interact under the most intense conditions. They teach us how black holes grow, how galaxies evolve, and how energy can shape the universe on large scales without occupying large volumes of space. This also explains why the question, "Are quasars the biggest objects in space?" is both understandable and misleading. The honest answer is no, they are not the biggest by size or mass, but they are among the most extreme by brightness and energy output. They occupy a unique category, one that does not fit neatly into simple rankings. Trying to force quasars into the label of biggest misses what actually makes them remarkable. Another layer to this discussion involves how we define objects versus systems. A quasar is not a standalone entity like a planet or a star. It is a system involving a black hole, an accretion disk, radiation, and sometimes jets. In this sense, asking whether a quasar is the biggest object is like asking whether a storm is bigger than a continent. A storm can be incredibly intense and influential without covering vast territory. Its power lies in dynamics, not size. When astronomers classify the largest things in the universe, they focus on structures like superclusters, filaments, and walls of galaxies. These structures define the cosmic landscape and contain enormous amounts of matter and space. Quasars, by contrast, are points of extreme activity within that landscape. They are important markers and drivers of change, but they are not the framework itself. This perspective helps resolve the confusion that often surrounds quasars in popular discussions. They are not cosmic kings ruling by size. They are cosmic engines ruling by intensity. Their light can travel across the universe and reach us from the dawn of time, but the region that produces that light is surprisingly small. This contrast is not a flaw in our understanding. It is one of the most beautiful and instructive features of the universe. By separating size from brightness, we gain a clearer picture of the cosmos. We see that the universe allows for many kinds of extremes. Some objects are extreme in scale, others are extreme in power. Quasars belong firmly in the second category. They remind us that the universe does not reward bigness alone. It rewards efficiency, concentration, and the relentless pull of gravity. As we move forward, this understanding opens the door to another fascinating aspect of quasars. Because they are so bright and so distant, they allow us to look deeper into the past than almost any other object. In the next part, we will explore how quasars act as cosmic time machines, revealing what the universe was like billions of years ago, and helping us reconstruct the story of cosmic evolution. Their size may be modest, but their role in uncovering the history of the universe is enormous. One of the most extraordinary things about quasars is not just how powerful they are, but what they allow us to see. Quasars are not only objects of energy, they are windows into time itself. When astronomers observe a distant quasar, they are not simply observing a faraway object in space. They are looking deep into the past, into an era when the universe was young, chaotic, and very different from the one we inhabit today. This is because light does not travel instantly. It moves at a finite speed and across cosmic distances. That speed turns space into a record of history. Every beam of light carries with it the moment of its birth, frozen in motion until it reaches an observer. To understand why quasars function as time machines, we must first understand what it means to look far into space. A light year is the distance light travels in 1 year, and even this immense distance is small on cosmic scales. Galaxies are separated by millions or billions of light years. When we observe a galaxy 10 million light years away, we are seeing it as it was 10 million years ago. When we observe a quasar 10 billion light years away, we are seeing it as it was 10 billion years ago, at a time when the universe itself was only a few billion years old. In this way, distance and time become inseparable. Looking farther means looking earlier. Quasars are uniquely suited for this task because they are so bright. Most ordinary galaxies become too faint to observe at extreme distances. Their light spreads out and weakens as it travels across expanding space. Quasars, however, shine with such intensity that their light can cross nearly the entire observable universe and still be detected. This makes them visible at distances where almost nothing else can be seen. Some of the most distant known quasars formed less than 1 billion years after the Big Bang, meaning their light has been traveling toward us for more than 13 billion years. This fact alone makes quasars remarkable. They allow astronomers to directly observe the early universe, not through simulations or theoretical models, but through actual light that originated during those ancient times. When scientists study the spectra of distant quasars, they are studying conditions that existed billions of years ago. The chemical signatures in quasar light reveal what elements were present in early galaxies, how gas was distributed in intergalactic space, and how matter evolved as the universe expanded. One of the most important discoveries enabled by quasars is the understanding of how quickly the universe changed after the Big Bang. In the earliest epochs, the universe was filled with neutral hydrogen gas, which absorbed much of the light traveling through it. As the first stars and galaxies formed, their radiation ionized this gas, making the universe transparent to light. This transition, known as the epoch of reionization, marks a major turning point in cosmic history. Quasars played a critical role in uncovering this period. By studying how quasar light is absorbed at different distances, astronomers were able to determine when reionization occurred and how rapidly it progressed. Quasar light also reveals the structure of the universe on the largest scales. As it travels toward us, it passes through clouds of gas and regions of varying density. Each of these regions leaves an imprint on the light, creating absorption lines that act like signposts along the journey. By analyzing these patterns, scientists can map the distribution of matter across billions of light years. This technique has allowed astronomers to trace the cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe. Beyond mapping structure, quasars help answer one of the most puzzling questions in cosmology. How did supermassive black holes form so early? Some quasars observed less than 1 billion years after the Big Bang are powered by black holes with masses of 1 billion suns or more. This presents a major challenge to our understanding of black hole growth. Under normal conditions, it should take far longer for black holes to reach such sizes. The existence of these early quasars suggests that the universe found ways to grow massive black holes very quickly, either through rapid accretion, the collapse of massive primordial clouds, or repeated mergers. By studying these ancient quasars, astronomers gain insight into the earliest stages of galaxy formation. Quasars are not isolated phenomena. They are deeply connected to their host galaxies. The presence of a quasar indicates that the galaxy has already accumulated a large amount of mass and gas. This means that massive galaxies existed much earlier than once thought. Quasars thus serve as markers for the formation of the first large cosmic structures. Another remarkable aspect of quasars as time machines is their ability to illuminate the invisible. Much of the universe is made of matter that does not emit light, including diffuse gas and dark matter. While dark matter cannot be seen directly, its presence influences how gas is distributed. Quasar light interacts with this gas, allowing astronomers to indirectly study regions that would otherwise remain hidden. In this way, quasars act like flashlights shining through cosmic fog, revealing the shape and composition of the universe across time. The study of quasar time travel is not limited to the distant past. Even relatively nearby quasars offer clues about how galaxies evolve over billions of years. By comparing quasars at different distances, astronomers can construct a timeline of quasar activity. This timeline reveals that quasar activity peaked several billion years ago and has declined since then. This decline mirrors the overall decrease in star formation across the universe, suggesting a deep connection between black hole growth and galactic evolution. This connection raises profound questions about cause and effect. Did quasars shape the universe, or did the universe shape quasars? The answer appears to be both. Quasars form in environments rich in gas and interactions, conditions common in the early universe. Once active, they influence those environments through radiation and powerful outflows. This feedback can regulate star formation, alter galaxy structure, and even affect neighboring galaxies. In this sense, quasars are not just passive markers of time. They are active agents in cosmic history. The ability of quasars to act as time machines also extends to fundamental physics. By observing quasar light that has traveled for billions of years, scientists can test whether the laws of physics have remained constant over cosmic time. So far, observations suggest remarkable consistency, reinforcing the idea that the same physical principles govern the universe across vast distances and ages. This stability allows astronomers to confidently use quasars as tools for exploring deep time. Quasars also help answer philosophical questions about our place in the universe. When we look at a quasar, we are seeing light that began its journey long before Earth existed. That light passed through space while galaxies formed, stars were born and died, and life slowly emerged on a small planet orbiting an ordinary star. The fact that we can now detect and analyze that light is a testament to both the vastness of the universe and the power of human curiosity. It is important to remember that quasars are not simply relics of the past. They are part of an ongoing cosmic story. While most quasars we observe are distant, quasar activity still occurs in the universe today, albeit less frequently. Studying both ancient and modern quasars allows astronomers to understand how conditions change over time and how similar processes can produce different outcomes depending on the environment. The time machine nature of quasars also reminds us that the universe is dynamic. It is not frozen in a single state, but constantly evolving. Galaxies grow, merge, and change. Black holes feed and then quiet down. Quasars flare and fade. By capturing these processes at different stages, quasars provide a timeline of cosmic evolution that would otherwise be inaccessible. As we piece together this timeline, a clearer picture of the universe emerges. The early universe was a place of intense activity, rapid growth, and extreme conditions. Quasars were more common because fuel was abundant and interactions were frequent. As the universe expanded and cooled, these conditions became rarer, leading to the quieter cosmos we observe today. This shift is written into the distribution and properties of quasars across space and time. Understanding quasars as time machines also deepens our appreciation of their role in science. They are not merely record holders for brightness. They are essential tools for exploring the universe's history. Without quasars, our view of the early universe would be far more limited. Many of the most important discoveries in cosmology, from the timing of ionization to the growth of large-scale structure, rely on quasar observations. As we move toward the next part of this journey, the focus will shift again. Having seen how quasars illuminate the past, we will examine how their immense energy affects the galaxies around them. In the next part, we will explore whether quasars can destroy galaxies, create new structures, or both. Their role as time machines shows us where the universe has been. Their role as cosmic influencers will show us how it continues to change. By now, we understand that quasars are not just bright lights in the sky. They are signs of extreme activity at the hearts of galaxies, powered by supermassive black holes consuming vast amounts of matter. But once we accept how much energy quasars release, a deeper and more unsettling question naturally arises. If a quasar can outshine an entire galaxy, what does that power do to the galaxy that hosts it? Does it tear the galaxy apart? Does it sterilize it, shutting down star formation forever? Or does it somehow help galaxies grow and evolve? In other words, are quasars cosmic destroyers, cosmic creators, or something more complicated than either label suggests? To answer this, we must first let go of the idea that galaxies are fragile objects. Galaxies are enormous systems, bound together by gravity and dominated by dark matter. They contain billions or trillions of stars, massive clouds of gas, and vast halos extending far beyond what we can see. A quasar, no matter how bright, is still only one component of this system. Its power is concentrated at the center, and its influence spreads outward in complex and uneven ways. Understanding this interaction requires us to think in terms of influence rather than simple destruction. The energy released by a quasar emerges mainly in two forms. One is radiation, including visible light, ultraviolet light, and X-rays. The other is mechanical energy, carried by fast-moving winds and, in some cases, powerful jets of particles traveling at near light speed. Both forms of energy interact with the surrounding galaxy, but they do so differently and with different consequences. The balance between these effects determines whether a quasar suppresses star formation, triggers it, or does a mix of both. Let us start with radiation. When a quasar is active, the radiation pouring out from its accretion disk can be intense enough to heat surrounding gas to extremely high temperatures. Gas is the raw material for making stars. When it is cool and dense, it can collapse under gravity and form new stars. When it is hot and energetic, it resists collapse. In many cases, quasar radiation heats the gas in the central regions of a galaxy so strongly that star formation slows down or stops entirely. This process is often referred to as quasar feedback. This feedback is one of the most important ideas in modern astrophysics. It helps explain why many large galaxies stop forming stars even though they still contain plenty of gas. Without some mechanism to heat or expel that gas, galaxies would continue forming stars indefinitely, which does not match what we observe. Quasars provide a powerful solution. By injecting energy into their surroundings, they can shut down star formation in the galaxy's core, effectively regulating the galaxy's growth. But radiation alone does not tell the full story. In many quasars, the energy output also drives massive outflows of gas. These outflows can take the form of winds moving at thousands of kilometers per second, pushing material away from the galactic center. Over time, these winds can remove huge amounts of gas from the galaxy altogether. This gas may escape into intergalactic space, never to return. When this happens, the galaxy loses the fuel needed to form new stars, leading to long-term decline in star formation. At first glance, this sounds like pure destruction. A quasar turns on, blasts its own galaxy, and shuts down its ability to create new stars. However, the reality is more nuanced. These same outflows can also compress gas in other regions of the galaxy. When gas is compressed rather than heated, it can collapse more easily and form stars. In this way, quasar activity can sometimes trigger bursts of star formation, especially in the outer regions of the galaxy or along the edges of outflowing material. Observations support this mixed picture. In some galaxies hosting quasars, astronomers see evidence of star formation being suppressed near the center, but enhanced farther out. The quasar acts like a powerful but uneven influence, reshaping the galaxy rather than simply destroying it. It is less like a bomb and more like a storm, disruptive in some areas and creative in others. Jets add another layer of complexity. When a quasar produces strong jets, those jets can travel far beyond the galaxy itself, interacting with gas in the surrounding environment. As they plow through space, they can heat gas, prevent it from cooling, and alter the structure of entire galaxy clusters. But jets can also create shockwaves that compress gas clouds, triggering star formation in regions far from the galaxy's center. In this way, a quasar can influence not just its own galaxy, but neighboring galaxies and the broader cosmic environment. This dual role of suppression and creation may seem contradictory, but it reflects a deeper truth about cosmic evolution. Many of the processes that shape the universe are not purely destructive or purely constructive. They do both, often at the same time. Supernova explosions, for example, can destroy nearby material, while also seeding space with heavy elements needed for planets and life. Quasars operate on a much larger scale, but the principle is similar. Another important point is timescale. Quasar activity does not happen all at once. It unfolds over millions of years, with periods of intense activity followed by quieter phases. During these cycles, the balance between destruction and creation can shift. Early in the quasar phase, when the black hole is feeding rapidly, the energy output may be strong enough to drive powerful outflows and suppress star formation. Later, as the activity declines, the remaining gas may cool and form stars again. This means the long-term impact of a quasar depends on how long it stays active and how much fuel it consumes. The relationship between quasars and galaxy evolution is also deeply tied to galaxy mergers. Many quasars are triggered by collisions between galaxies. When galaxies merge, their gas is disturbed and driven toward the center, feeding the black hole and igniting quasar activity. At the same time, these mergers often trigger intense bursts of star formation. In this scenario, the quasar is part of a larger transformation. The galaxy is already changing, and the quasar both responds to and influences that change. This perspective helps explain why massive galaxies often host large black holes and show signs of past quasar activity. The growth of the black hole and the evolution of the galaxy are linked. The quasar phase acts as a regulating mechanism, preventing the galaxy from growing too large or forming stars too rapidly. Without this regulation, galaxies might become unrealistically massive and bright, inconsistent with what we observe in the universe today. Importantly, quasars do not destroy galaxies outright. There is no evidence of a quasar completely tearing a galaxy apart or erasing it from existence. Galaxies are simply too massive and too strongly bound by gravity for that to happen. Even the most powerful quasar affects only certain components of the galaxy, mainly the gas. The stars themselves, which make up most of the visible mass, are largely unaffected by quasar radiation and winds. They continue orbiting the galaxy's center as before. This distinction is crucial. When we talk about quasars destroying galaxies, we are really talking about their ability to shut down star formation, not their ability to eliminate galaxies. A galaxy with no star formation is still a galaxy. It becomes quieter, redder, and more stable, but it does not disappear. Many of the large elliptical galaxies we see today may be the end products of this process, shaped in part by ancient quasar activity. Quasars also influence the universe beyond individual galaxies. Their energy contributes to heating intergalactic gas, affecting how matter clumps together on large scales. This heating can delay the formation of new galaxies in certain regions, while allowing others to grow more easily elsewhere. In this way, quasars help shape the large-scale structure of the universe, even though they are relatively small in physical size. It is also worth considering what quasars do not do. They do not create matter from nothing. They do not build galaxies directly. Their creative role is indirect, operating through pressure, compression, and regulation rather than construction. They shape the environment in which galaxies and stars form, influencing outcomes without dictating them completely. From a broader perspective, quasars can be seen as part of the universe's self-regulating system. Gravity pulls matter together, forming galaxies and black holes. As black holes grow and become active, they release energy that pushes back, preventing unchecked collapse. This balance helps maintain the structure we observe today. Without quasars and similar feedback processes, the universe would look very different, likely dominated by overly massive, overly dense galaxies. This balance also highlights why quasars are most common in the early universe. In that era, matter was more abundant, galaxies were closer together, and interactions were frequent. The conditions for extreme growth and extreme regulation were in place. As the universe expanded and settled, these conditions became rarer and quasar activity declined. The universe moved from a violent, energetic youth into a calmer maturity. Understanding whether quasars destroy or create galaxies ultimately leads us to a more subtle answer. They do neither in a simple sense. They transform galaxies. They regulate growth, redistribute matter, and influence long-term evolution. They are not villains or heroes, but powerful forces embedded in the cosmic system. This realization also reframes how we think about cosmic power. True influence in the universe does not come from obliteration, but from regulation. Quasars are influential not because they erase galaxies, but because they guide how galaxies evolve over billions of years. Their legacy is written into the structure of the universe itself. As we approach the final stages of this journey, the focus will shift once more. Having explored quasars as engines, time machines, and galactic influencers, we will turn to a more personal question. Do quasars pose any danger to us? Could their immense energy ever threaten Earth or life in the universe? In the next part, we will separate fear from fact and explore what quasars truly mean for our cosmic safety. Whenever humans learn about something immensely powerful in the universe, a natural question follows almost immediately. If quasars are among the brightest and most energetic phenomena ever discovered, could they be dangerous? Could one harm Earth, sterilize life, or disrupt the stability of the universe as we know it? These questions are not driven by ignorance or panic. They are a normal response to understanding scale. When faced with forces that dwarf anything on Earth, the mind searches for personal relevance. To answer these questions properly, we must move carefully, separating cinematic imagination from physical reality. The idea of quasars as cosmic threats often comes from how they are described. Words like monster, engine, and cosmic lighthouse create images of something aggressive and uncontrolled. In movies and fiction, Powerful energy sources are frequently portrayed as destructive beams that can wipe out planets or entire civilizations. But the universe does not operate according to storytelling logic. It operates according to distance, direction, energy dispersion, and time. Once we understand these factors, the fear surrounding quasars begins to fade. The first and most important factor is distance. Quasars are incredibly far away. Almost all known quasars are located billions of light years from Earth. This is not a coincidence. Quasars were far more common in the early universe than they are today. The closest known quasar is still hundreds of millions of light years away. At such distances, even extraordinary amounts of energy spread out over enormous volumes of space. By the time quasar radiation reaches Earth, it is incredibly weak, far weaker than the sunlight we receive every day. To put this into perspective, consider how light behaves. Light spreads out as it travels. The farther it goes, the more diluted it becomes. This is why a flashlight looks bright nearby, but faint from far away. Even the most powerful lighthouse becomes invisible at great distance. A quasar is unimaginably powerful at its source, but its light must travel across billions of light years of expanding space. By the time it reaches us, it is harmless. We detect it only with sensitive instruments, not with our eyes or our skin. Another critical factor is direction. Quasars do not emit energy evenly in all directions. While their accretion disks emit radiation broadly, their most intense energy often comes in the form of narrow jets. These jets are focused streams of particles and radiation launched along the black hole's rotational axis. They behave like cosmic spotlights, not explosions. For a jet to pose a danger to Earth, it would have to be precisely aligned with our planet across an unimaginable distance. The odds of this alignment are extremely small, and there is no evidence that such a scenario has ever affected Earth. Even in the unlikely case that a quasar jet were pointed toward Earth, distance would still protect us. The energy would spread and weaken over time. Additionally, Earth is shielded by its atmosphere and magnetic field, which block or deflect many forms of high-energy radiation. Our planet has survived countless cosmic events over billions of years, including nearby supernova and intense solar storms. A distant quasar would not pose a greater threat than these known and manageable phenomena. It is also important to recognize that quasars are not sudden events. They do not turn on instantly like a bomb. They develop over long periods as black holes gradually accumulate matter. Their activity unfolds over millions of years. This slow timescale matters. Sudden bursts of energy are more dangerous than gradual changes. A quasar's energy output, while immense, changes slowly on human timescales. There is no scenario in which a quasar suddenly ignites and wipes out life without warning. Some people worry about quasars because they are associated with black holes, which are often misunderstood. Black holes are frequently imagined as objects that consume everything around them, growing endlessly and threatening the universe. In reality, black holes are limited by their environment. They cannot consume matter faster than it falls toward them, and they do not roam freely through space. The supermassive black holes that power quasars are anchored at the centers of galaxies. They are not approaching Earth, and they never will. Another common fear involves radiation. Quasars emit large amounts of ultraviolet and X-ray radiation, which can be harmful to living organisms. But again, distance matters. Radiation intensity decreases rapidly with distance. The radiation from quasars that reaches Earth is negligible compared to radiation from the Sun, cosmic rays, or even medical imaging equipment. Life on Earth has evolved under constant exposure to cosmic radiation, and distant quasars contribute only a tiny fraction of that background. It is also worth considering Earth's long history. Life has existed on this planet for billions of years. During that time, the universe was far more active than it is today. Quasars were more common, Galaxies were colliding more frequently, and energetic events were more widespread. Despite this, life not only survived but flourished. This historical fact alone strongly suggests that quasars do not pose an existential threat to life in the universe. There is, however, a subtle and interesting question worth exploring. While quasars are not dangerous today, could they have influenced the development of life in the distant past? Some scientists have speculated that intense radiation from nearby quasars in the early universe could have affected the chemistry of young planets or the evolution of early life. This remains an open area of research. Even so, such effects would be indirect and highly dependent on proximity and timing. They would not resemble the dramatic destruction often imagined in fiction. Another layer of fear comes from misunderstanding scale. Humans are used to thinking in terms of cause and effect on short timescales. We imagine danger as something immediate and local. The universe, however, operates on scales of millions and billions of years. Quasars influence galaxies gradually. Their effects unfold slowly, shaping long-term evolution rather than causing sudden catastrophe. This difference in timescale makes them feel abstract and frightening, but it also makes them safe. It is also important to distinguish between hypothetical extremes and realistic scenarios. In theory, a quasar located very close to a planet with a jet directly aimed at it could cause serious damage. But such a scenario would require an extraordinary set of conditions. The planet would need to be extremely close to the quasar's host galaxy, aligned perfectly with the jet and present during the quasar's most active phase. Given the vastness of space and the rarity of quasars today, this scenario is effectively non-existent for Earth. In contrast, there are cosmic phenomena that do pose real, though still small risks. Asteroid impacts, solar flares, and nearby supernova are far more relevant to Earth's safety than quasars. These events are closer, more frequent, and better understood. By comparison, quasars are distant background features of the universe, fascinating to study but irrelevant to daily life on Earth. Understanding this helps reframe our relationship with the universe. Not everything powerful is dangerous. Power alone does not determine threat. Distance, direction, and context matter just as much. Quasars are powerful because they operate under extreme gravitational conditions, not because they are hostile forces. They are not cosmic villains. They are natural outcomes of galaxy evolution. This realization also highlights an important truth about science communication. Sensational language attracts attention, but it can distort understanding. Describing quasars as threats may be exciting, but it does not reflect reality. A calmer, clearer explanation reveals something more meaningful. The universe is vast, energetic, and sometimes violent, but it is also stable enough to support long-term structures and life. Quasars are part of that balance, not a disruption of it. In many ways, the fear of quasars says more about human psychology than about the universe itself. We are drawn to extremes and danger. We imagine ourselves at the center of cosmic events. Science teaches us humility. Most of the universe exists far beyond our reach, indifferent to our presence. Quasars shine across space and time, not to threaten us, but simply because physics allows them to. By removing fear from the discussion, we gain a clearer appreciation of what quasars truly represent. They are laboratories of extreme physics, markers of cosmic history, and engines of galactic evolution. They are not weapons, warnings, or harbingers of doom. They are part of the universe's natural complexity. As we approach the final part of this journey, the focus will shift from fear to understanding. We will gather everything we have learned and return to the central question that started it all. What are quasars really? What do they teach us about size, power, and our place in the universe? And why does understanding them matter, even if they pose no danger to us? The answers to these questions will bring this exploration to a thoughtful and satisfying conclusion. After traveling through discovery, confusion, power, scale, time, creation, and fear, we arrive at the place where every good scientific journey must end: understanding. Quasars are no longer strange points of light or exaggerated cosmic monsters. They have become something more meaningful and more honest. They are extreme, but they are also natural. They are powerful, but they are also precise. And most importantly, they teach us something essential about how the universe truly works. At the very beginning of this exploration, we asked a simple question that turned out to be far deeper than it first appeared. What is a quasar, and is it really the biggest object in space? Along the way, we discovered that the difficulty in answering this question comes not from the universe being unclear, but from our human tendency to mix different ideas together. We confuse brightness with size. We confuse power with mass. We confuse visibility with dominance. Quasars force us to untangle these ideas because they break our intuition while perfectly obeying the laws of physics. A quasar, at its core, is not a thing in the way a planet or a star is a thing. It is a process. It is a phase. It is a moment in the life of a galaxy when the conditions are right for something extraordinary to happen. Gas falls inward toward a supermassive black hole. Gravity accelerates that gas to extreme speeds. Friction and motion convert mass into energy with astonishing efficiency. Light is released in quantities so large that it can cross the observable universe and still be detected. That is a quasar. No magic, no mystery energy, just gravity, motion, and time operating at their limits. This understanding alone answers part of the original question. A quasar is not an object that fills space. It does not stretch across millions of light years. It does not define the structure of the universe. In terms of physical size, quasars are small. Even the largest quasar-producing regions are tiny. Compared to galaxies, clusters of galaxies, and the vast cosmic filaments that form the universe's backbone. The biggest structures in space are not bright points of light. They are quiet, massive networks of matter extending across hundreds of millions of light years. And yet, despite being small, quasars dominate attention. They dominate observation. They dominate records. They are the brightest sustained objects ever observed. They outshine entire galaxies. They make distant corners of the universe visible. This is where the deeper lesson emerges. The universe does not reward size alone. It rewards efficiency. It rewards concentration. It rewards extreme conditions. Quasars are proof that power does not need to be spread out to be overwhelming. It can be focused, it can be compact, it can be precise. When astronomers first encountered quasars, the shock was not just about brightness, it was about what that brightness implied. It implied black holes that were far more massive than expected. It implied galaxies forming earlier than expected. It implied that the early universe was far more active and violent than anyone had imagined. In this way, quasars did not just add a new object to astronomy. They forced astronomy to grow. They forced scientists to accept supermassive black holes as real, common, and central to galaxy evolution. They forced new theories of how matter behaves under extreme gravity. They forced a rethinking of how galaxies grow, how they stop growing, and how energy flows through cosmic systems. Few discoveries have reshaped so many areas of science at once. Quasars also changed how we understand time. Because their light travels for billions of years, quasars allow us to see the universe as it once was. They act as markers of cosmic history, revealing when galaxies formed, when black holes grew, and when the universe transitioned from darkness to light. Without quasars, much of the early universe would remain invisible. They are not just bright objects. They are storytellers, carrying information from the deep past to the present. This ability to look backward through time brings perspective. It reminds us that the universe has a history far longer than human civilization, longer than Earth itself. Quasars were blazing when our planet did not yet exist. They shone when the first stars were forming. They faded as the universe matured. In that sense, quasars are witnesses to cosmic adolescence, moments of intense growth and transformation that shaped everything that came after. Another important truth revealed by quasars is balance. The universe is not purely constructive or purely destructive. It is regulated. Quasars do not simply destroy galaxies, nor do they simply create them. They regulate them. They slow star formation when it becomes too intense. They redistribute gas. They influence the environments in which stars and planets form. This regulation helps explain why galaxies look the way they do today. Without quasar feedback, the universe might be filled with unrealistically massive chaotic galaxies that bear little resemblance to what we observe. This regulatory role also answers the fear-based questions that often surround quasars. Are they dangerous? Could they harm Earth? Could they wipe out life? The evidence tells us no. Quasars are distant, directional, and slow in their effects. They operate on scales far removed from human experience. Life on Earth has existed through periods when quasars were far more common than they are today. Their power is real, but it is not personal. It is not targeted. It is not hostile. Understanding this replaces fear with appreciation. Quasars are not cosmic threats. They are cosmic tools. They allow us to test physics under extreme conditions. They allow us to map the universe's structure. They allow us to study the growth of black holes and galaxies together. They allow us to confirm that the laws of physics have remained consistent across billions of years and unimaginable distances. Perhaps the most important lesson quasars teach us is humility. They show us that the universe does not conform to human expectations. Something can be small and overwhelmingly powerful at the same time. Something can be invisible and yet define the behavior of entire galaxies. Something can be temporary and yet leave permanent marks on cosmic history. Quasars remind us that intuition is not enough. Understanding requires patience, evidence, and a willingness to revise what we think we know. So, is a quasar the biggest object in space? The honest answer is no. The biggest objects in space are vast structures made of countless galaxies and enormous amounts of dark matter. But if the question is really about extremes, then quasars earn their place. They are the brightest sustained sources of light. They are among the most energetic phenomena ever observed. They represent the universe at its most intense. And maybe that is the deeper reason quasars fascinate us. They sit at the edge of what seems possible. They remind us that the universe is capable of far more than we imagine. They challenge our definitions and force us to think carefully about what words like big, powerful, and important actually mean. In the end, quasars are not about being the biggest, they're about being the most revealing. They reveal how gravity can dominate energy production. They reveal how black holes and galaxies grow together. They reveal how the early universe evolved. They reveal that the cosmos is not static, but alive with processes that shape it over billions of years. As humans, we live on a small planet, orbiting an ordinary star in an average galaxy. Quasars remind us that even in such a vast universe, understanding is possible. Light can travel across time. Information can survive cosmic distances. Curiosity can bridge the gap between the human mind and the deepest workings of the universe. And perhaps that is the most meaningful conclusion of all. Quasars are not just objects to be ranked or feared. They are reminders that the universe is knowable even when it is extreme. They show us that asking the right questions matters more than clinging to simple answers. They invite us to keep looking, keep learning, and keep wondering. The universe is not defined by what is biggest or brightest alone. It is defined by relationships, processes, and time. Quasars sit at the crossroads of all three. They are brief, brilliant chapters in the universe's long story, And by understanding them, we understand a little more about the universe and a little more about ourselves. As we come to the end of this journey, take a moment to let the scale of what we explored really sink in. Quasars are not just distant points of light. They are reminders that the universe can concentrate unimaginable power into surprisingly small places. They show us that size does not always decide importance, and brightness does not always mean dominance. Sometimes, the most influential forces work quietly at the center, shaping everything around them over millions of years. We began with a simple question: what is a quasar, and is it really the biggest object in space? Along the way, we discovered that the real answer is more interesting than a simple yes or no. Quasars are not the largest structures in the universe, but they are among the most extreme. They are powered by gravity itself, fueled by supermassive black holes, and bright enough to let us see into the earliest chapters of cosmic history. Without quasars, much of the universe's past would remain hidden from us forever. What makes quasars truly special is not just how powerful they are, but what they teach us. They teach us how galaxies grow and change. They teach us how black holes shape the universe without ever shining themselves. And they teach us that the universe is not static. It is active, evolving, and full of processes that operate far beyond human intuition. If this video changed the way you think about space, even a little, then it has done its job. If it made you pause, wonder, or look at the night sky differently, that curiosity is exactly what drives science forward. The universe does not reveal its secrets easily, but when it does, the answers are always deeper than we expect. If you enjoy deep, calm, and meaningful explorations of the cosmos like this one, consider subscribing to the channel. New videos here don't rush. They don't oversimplify. They take the time to explain the universe as it really is. If you found value in this journey, tap the like button so more people can discover it too, and share it with someone who loves space as much as you do. Thank you for staying until the end. And remember, the universe is far bigger, older, and more fascinating than we can ever fully imagine. Until the next journey, keep looking up.